We'll get on to the main purpose of the meeting tonight, and it's a talk by Alan Richardson here, who has for many years was a senior lecturer at Halesowen College, but he's got a great knowledge of and been working on the geo-conservation at the Lickey Hills, and he knows a great deal about it. So his talk tonight is about the geology of the Lickey Hills. So, Alan, thank you.
Yeah, as Alan said, I've been teaching for, well, I taught for 35 years. I did 4 years at the Crestwood School at King's Winford teaching A-level geology, and then moved to Halesowen College where I set up my own geology department, teaching A-level again. And on the way I've also tutored with the Open University and been a visiting tutor for the Field Studies Council in the Lake District. And then 11 years ago I retired and became an amateur geologist. So what does an amateur geologist do? Is there any contribution that the amateur can make? And we're on the southern outskirts at Lickey, we're on the southern outskirts of Birmingham. It's a city with a well-established university with a geology department that's run since the 19th century. So is there anything new that we could find out about the geology with just nothing more than hammer and hand lens that would add to our understanding of the geology? Well, when I retired, I didn't think so. But an ex-student of mine introduced me to geoconservation. And in this case, this group of ne'er-do-wells, and you may certainly recognize Julie there, who is the energy and drive behind the entire group. And without her, I don't know how we'd operate, to be honest. So this is one of several groups that was set up in 2008 under the name Geo-Champions by the Hereford and Worcestershire Earth Heritage Trust. And they quote that between all the groups across the two counties, we cover 19 locations. Well, we've added locations since we've been working, and it's now more than that because of the number that we do. But it's a rather small group, and if any of you are feeling energetic and want to save on your gym membership, come and join us. So the area we cover is south of Birmingham, and we've got the Lickey Hills here, and this is Birmingham up here. Most of what we cover is within the confines of the Lickey Hills Country Park, just here. But we've also got an important site at Rubery, and our interest extends a bit further north, but we don't cover the sites up here. So it's easy to get to, just adding that, just in case you want to come and join us. And if we look at the Google Earth image of it, north is over in this direction. This is the main ridge of the Lickey Hills, and most of this area is the Lickey Hills Country Park, and most of our sites lie within that. We've got one other site up here in Rubery, which we'll have a look at shortly, in the road cutting of the A38 and round the corner in Leach Green Quarry. So if we do a bit of magic and overlay the BGS map on top of it, we can see what lies beneath. The Lickey Ridge itself is here, and you can see the LQ for Lickey Quartzite. It's bounded to the west by the Leach Heath Fault and to the east by the Rednall Fault. So this is Ordovician in age, Ordovician quartzite, and it's an inlier surrounded by younger rocks. And the younger rocks are down-faulted on either side, so the Lickey Ridge itself constitutes a horsed block. At the southern end, there's another faulted contact. The green is Barnt Green volcanics, which are lower Ordovician, and there's a little slice of Wenlock limestone in here. We've got carboniferous rocks, and then Permian, Clint breccia, and lower Triassic conglomerates. On the opposite side, to the east, we've got all Triassic sediments. This is what used to be called Kidderminster Formation, now Chester Formation. Don't try and remember it, it'll change next week, probably anyway. And over here, we've got Bromsgrove Sandstone. This looks as though it's the same colour as the Lickey quartzite, but in fact it isn't. Those little spots denote a different formation. This is the Upper Llandovery, Silurian, Rubery, sandstone and shale. And there's another little patch of it over here. Structurally, to the west is the Worcester Basin, and to the east, the Knoll Basin. So we've got downfaulting on either side of the ridge. The Lickey Ridge sites. This is a view of the Leach Heath quarry, which we don't have access to, but it gives you an idea about the general nature of what we find in the Lickey Hills. The Lickey quartzite is very competent, very hard, but very brittle rock. So it was quarried for roadstone. Up until most of the quarries closed in the 1920s, but one of them did continue up into the 1970s. As I say, it's very competent, it fractures readily, but it's hard and resistant. And one of the features of it is we've got well-defined partings of clay-rich sand, or if you like, sandy clay, whichever. But those layers have largely controlled the structural response of these rocks to the forces that have acted on them. So we cover all of these sites. Well, yes, we do. And during the time since I've been there, we've got a lot of them registered as local geological sites. There is a fly in the ointment, a very big fly in the ointment, and that is Birmingham. Our southern sites all lie in Worcester, and they've got a great setup for registering these sites as local geological sites. You write a proposal, it goes before a committee of geologists with some representatives of the planning department there, and I was going to say they say yay or nay. I've never known them say nay. And it gets status as an LGS, and then we stick it on the website and everyone can find it. Birmingham's got a different system. They have slinks and sinks, sites of local interest for Nature Conservancy and sites of interest for Nature Conservancy. And it's a great acronym. It's so apt because you put a proposal in, it disappears off into the ether, you don't represent it at a meeting, and in this case, I put 2 proposals in for sites that fell in the Birmingham side. Unfortunately, they both lay within a site of interest for Nature Conservancy for the heathland vegetation there. And so they didn't get a separate listing, they just got incorporated into that. Don't waste time trying to find those sites on Birmingham's website. You'd have to look under biodiversity to find it anyway, and the chances are you never would find it. So a sink is essentially what they did to them. They've sunk without trace. So these are the sites that we're going to be exploring, and as you can see, they cover the length of certainly the southern part of the Lickey Ridge. Right, let's have a look at the historical references to it. Lapworth in the 19th century describes it there as a thick mass of quartzite and very similar in its general characters to the Hartshill quartzite at Nuneaton. And that is Cambrian. And so it was misidentified as being Cambrian because it looked like that. But quartzites, I mean, there's so much variation in the quartzite in the Lickey Hills anyway, you could correlate it with almost any quartzite you choose to look at. At the bottom there, this Lickey quartzite is much folded, jointed and shattered. Neither the base nor the summit of the formation is exposed, and the disconnected sections do not afford a sufficiency of evidence to enable us to construct a complete ascending succession. Yes, it's a big lump of quartzite, but it's complicated. More recently, the Redditch memoir says much the same. Hard, brittle, jointed, shattered rock. At Rubery, it's overlain unconformably by the Rubery sandstone. So we know that it can't be older than, it can't be younger than that. It has to be older than the Rubery sandstone. That gives us some dating reference in it, at least. The base of it is a bit of a guesstimate. In what we believe to be the oldest part of the Lickey quartzite, there's a lot of tufaceous material of volcanic origin. And the slightly older, we believe, burnt green volcanic formation could be the source of this tufaceous material. So the Lickey quartzite could have come just after the eruptions that produced the burnt green volcanic sequence. And that has been dated. So by extension, we think that the base of the Lickey quartzite is lower Ordovician of a similar but slightly younger age to the burnt green formation. So let's have a look, first of all, then, at the Rubery cutting up here and see what we find there. And this is a really nice outcrop. This is, as far as I know, Birmingham's only local nature reserve for geology. Hooray! And you can see how much care they take, because this cutting goes all the way up, or beyond the door, and it's completely overgrown. And part of the LNR is Leach Green Quarry up here, which was a nice quarry, a good quarry face, lots of interesting things in it. And to preserve it, they put a fence just to the right of where we're looking, so that they could build houses in front, and then they left it. And it's completely overgrown, and of course, because it's derelict, all the houses use it as their domestic rubbish dump, and it's full of trash. So it's not very convenient. But this lovely clean bit here is what the Lickey Hills Geo-Champions scrub on a regular basis. And if we look at it, we can see this is slightly enhanced. I've made the Lickey quartzite itself slightly paler digitally, so you can see the boundary between. So this is the Rubery formation above, Silurian, and the Ordovician Lickey quartzite below. Notice in the foreground the pressure washer. Every geoconservation group needs a pressure washer. Look at the difference. That's where the washing ended. So all of this black grime was covering all of this, and it's all been washed off. And it's a much gentler process than scrubbing it with brushes. You use the brushes to get rid of the lichen and the mosses, and then pressure wash it, and it comes up in such a way that you're seeing things that nobody else has seen before in many cases. And in fact, a lot of the discoveries we've made, we wouldn't have seen without the pressure washer. And if we zoom in and have a closer look, you can see that, as I say, the surface is very irregular, this erosion surface. And look at the hollows, they're full of pebbles, well-rounded pebbles, and we've got cobbles like this of some considerable size. So this was an energetic environment in which all of this was being deposited on an eroded surface of already well-jointed Lickey quartzite. So the jointing we see in the Lickey quartzite had already been imparted through deformation before uplift and erosion and deposition of the Rubery. And the sequence was logged by Wills in the 20s. And down the bottom right, that's the bit we were looking at just, and that little structure there we'll have a look at in more detail in a moment. But he's logged the whole sequence and collected fossils, and it's on the basis of the fossils that it's been dated to Llandovery. And so this is 3 sections. I hope you can see that this bit ends there and it continues along there. And of course, all of this, access to all of this is missing apart from the tiny little bit down here. This is that feature that I just pointed out on the section. And Wills identified it thus: a joint in quartzite filled with Llandovery sandstone. He didn't have the pressure washer. If you look at it here, this fill, after washing, you can see that it's full of fragments, angular fragments of the Rubery sandstone with a softer matrix of sand. And you've got these subhorizontal striations on the side wall indicating that in fact it's a strike slip fault filled with a fault breccia. So rather than a joint, it's a fault. Movement has occurred along it. Going round the corner into Leach Green Quarry, I recently went in with Dr. David Ray, who some of you may know. He's just recently completed a paper looking at the rates of sea level change in the Silurian, and he wanted to get some data from here. So we picked our way through the vegetation, crunching over fluorescent tubes and goodness knows what else underfoot. And we've cut down vegetation in places. So you can see here where we've cut down a gorse bush. And across this section, the unconformity is fairly flat, but we've got features like this in it, which is lovely. If we look a bit closer, we've got this channel feature full of pebbles and cobbles, some of quite considerable size. This is a big lump of nicely rounded quartzite. I wouldn't swear to it being Lickey quartzite. Maybe it's the Hartshill quartzite. Goodness knows. But again, these are well-travelled pebbles. To get that degree of rounding, they've moved some distance. And of course, all of this is really not accessible in general, which is a shame. So, moving on. That's the top of what we can see in the Lickey quartzite. At the other end of things, the Redditch memoir makes reference to tufaceous material, so of volcanic origin, most commonly in what are probably the oldest beds exposed, and there may be an upward passage from the Barnt Green volcanic formation. But remember, it's a faulted contact, so we can't see this passage upwards. So we're looking down at this end of the Lickey Hills now. This is the Barnt Green formation, and you can see this faulted contact. And this is what it looks like. This is at Kendall End Farm, and this is a rig site, but I've never had access to it. We haven't negotiated access to it since I've been in the group, but it's there. So that's down here, that quarry. Sorry, I beg your pardon, it's down here. This is Kendall End Farm, so it's down here. If we go to Barnt Green Road Quarry, we find what we think are the oldest exposed beds of the Lickey quartzite. This is what they used to look like, and I wish it was still like this, where you could just walk up a bedding plane like this chap's done. So this is when it was still a working quarry. And you can see what most people make a big noise about is this recumbent fold in it, which is very nice. As I mentioned before, a lot of the structures are controlled to a large extent by the clay-rich layers within the Lickey quartzite that cause it to behave the way it does. And this is just a polished surface of Lickey quartzite. And you can see that it's quite red. There's a lot of iron in it. And these white crystals are all feldspars. So it's a very immature sediment. And in this particular layer, you can see that it goes much, much finer. And then we've got this very well-defined dark layer, which when you look at it from above, is packed full of muscovite mica. And then above it, this would be clay, or at least clay-rich sand. Soft, you can poke it, you can pull lumps out, in contrast to the very hard Lickey quartzite itself. Remember that. This is the right way up for this sediment, and at the top of the layer, we go to very fine material and a very mica-rich layer before going into clay, because much, much later in this talk, I'll make reference back to that. This is the thin section of the material. This is silt in a clay matrix, and this is more or less pure clay. But you can see from these lenticular structures within it that it's been sheared. There's been movement along that bed. And it's this movement, these clay-rich layers allow the beds of quartzite to slide against one another. This is a general view of the quarry. If any of you are interested and you want to look at this in more detail, you can go on the Lickey Geo-Champions website, or the Geo-Champions website, and look for the Lickey section. And this is a gigapan image. So it's a composite of a few dozen photographs that I took that have then been stitched together. So you can zoom in to a considerable degree and get more detail. First of all, let's have a look at the fold up here a little more closely. And at first glance, it looks very much like a very straightforward fold. But you'll notice in the hinge of the fold, there's a lot of shattering of the rock, because, of course, you're bending brittle rock very tightly there, and it's going to break, and the layers are sliding against one another. So you get a lot of disruption in that area. So this is a model that demonstrates the sort of thing that's going on. These layers are separated by clay-rich horizons, which allow them to slide against one another. So you can get quite tight folds with intense jointing where it's flexing and breaking. The other end of the quarry is where it gets a lot more interesting. This is the southeast corner, and at first glance, you might be tempted to think it's a simple, oh, if I can get this cursor to move the way I want it to, an anticline, but it's not. If we look more closely at this area, and this is the area that we keep cleaning because it's the most interesting, I think. You've got beds dipping towards you here and towards you here, but these beds are dipping to the left. So we'll go to this area and look more closely. Along here, near where my scale is, this is a fault, and you can tell because it's all brecciated, it's all angular fragments. And if you follow it up there, it stops being brecciated. Now it's just normal bedding. But the dislocation steps across, and you can see brecciation in these layers, and then intense brecciation over here. So the fault is actually stepping across here. If we go up and to the right and look at this area, we've got the same sort of thing going on here. There, you can see bedding coming down here and meeting bedding that's dipping towards us. So we've got a step over there as well. And in fact, we've actually got the hinge of the fold in here. And we're going to look at that a little more closely in that area. And I've highlighted areas of brecciation. So we can see bedding here coming down, and then the bedding is now going in a different direction. This is the hinge of the fold, but it's been crushed and brecciated in there. But there's also breccia along these planes here, so there's been movement along these as well. So, my second interpretation of this outcrop looked like this, with footwall block. So the red shows the main movement surface, with the hanging wall block moving away from us towards the south, with movement along here, then stepping across, and bits of movement across here. And on this side, the movement is following those clay-rich layers in this direction. However, there's a problem with this. the fold, it would be reasonable to suppose that the forces that generated the fold also caused the fault movement. But look at the sense of the fold. It's a Z-shaped fold, and it shouldn't be. If the movement was this way, it should be an S-shaped fold, which I can demonstrate thus. There's your S-shaped fold. So that's what should have happened if that hanging wall block was moving away from us towards the south. So if we have it moving towards us, towards the north, then it's consistent with the folding. But of course, there's a space problem. How do you push it down into solid rock? Well, just set that aside, because it works like this. I'll just brush aside the space problem. I've got some supporting evidence. Down in this corner, I was out one day on my own looking at this, and in that area next to my scale rule, I saw these very fine striations. You can see them going in this orientation, and also little steps in the surface, suggesting that these are slickened sides caused by the hanging wall block moving towards us, downwards across that surface. I refer to these as fairy slickened sides because I'd never seen them before, and I've been back since and never seen them again. So they just decided to make themselves apparent to me to help me along. And I've put chalk marks on them indicating the orientation and sense of direction that I observed at the time. So it seems to support the idea, space problem aside, that the hanging wall block was moving northwards. Like this. So, a reinterpretation. But notice if the fold hinges there, these rocks are the right way up, and these rocks are inverted. And notice the orientation there, 159.60 northeast. Because now we're going to leave Barnt Green Road Quarry and go to Kendall End Quarry. This is a polished surface of the rock in Kendall End Quarry. And you can see it looks more mature, there's a lot less feldspar, but bear in mind, where you've got these little cavities, that's where feldspar has weathered out. And you've still got some white feldspars intact. But it's a fairly mature sediment, it's well sorted, and of course very well cemented. In terms of sedimentary structures, we've got some large-scale ripples. But are they? Because look at the strike and dip. This is what we had in Barnt Green Road Quarry. This is an average of 9 readings in Kendall End Quarry, and they're very similar. If that's a reading from inverted beds in Barnt Green Road Quarry, it seems very likely that these rocks, having exactly this, well, more or less the same orientation, are inverted as well. So if I then go back to this, are those sedimentary ripples, or are those the ripples, and these lenticular masses, are they just the sedimentary fill between crests, in the hollow between large ripples? And the whole lot's inverted. Now, I mentioned before that in the Barnt Green Road Quarry, we've got that layer that gets finer and finer, and then there's a mica layer, muscovite layer, before you go into clay. Well, just around the corner here, we've got one of these clay layers, and the mica-rich layer is above it rather than below it, which tends to support the idea that the rocks in Kendall End Quarry could be upside down. Now, going back to this view, we've got the ridge, the main ridge going here, and then it's transected at this point by a deep Lickey gorge, sometimes referred to as the Rednall Gorge. So it's quite a steep-sided valley, and on the north side of that we've got Rose Hill Quarry. This was described by Bolton in the 20s, and he drew this sketch showing thrusts with some really quite impressive drag folding on them. We've not seen these drag folds. That might be because he does say it's at the base of the quarry, and therefore there's quite an accumulation of quarry spoil at the base of the faces, so they might be covering this. However, we have identified at least 2 thrusts. They're difficult to spot because the movement planes are following these clay-rich layers, but you find that the clay is packed with angular fragments which have been broken off as the adjacent beds have moved past one another. And in places, they'll step across a bed into another plane of movement. And if we look at the lower thrust plane, just round the corner in a more accessible part of the quarry, this is the movement plane, this pale layer at the bottom. And you can see that it's packed with angular fragments of Lickey quartzite. And immediately above it, you've got these inclined fractures of an imbricate zone, suggesting that the hanging wall block, the overlying rock, has moved away from us in this direction. More convincingly, I think, is this outcrop just around the corner. I've coloured the footwall block with this reddish colour to distinguish it. And again, we've got one of these clay-rich layers going along here with lots of angular fragments of Lickey quartzite. And again, these much larger inclined fractures of an imbricate zone, which we can use to interpret the thrust direction, which is northwards, consistent with my more recent interpretation of what we saw in the Bark Green Road quarry, of the overlying rocks being pushed northwards. And in the west bay of Rose Hill Quarry, we see this. You can see where I've been with the pressure washer, where the green has disappeared. So these are the pressure washed bits, because these are fissures, which we'll come back to later. But significantly at this point is this movement plane. Again, it's following a clay-rich band, and you can see it climbing up over the top. So again, suggesting a northward movement of the hanging wall block. Right. Let's leave structure and consider fossils. Don't get excited, you'll be disappointed. Lapworth says, no fossils except worm burrows. He didn't have the courtesy to tell us where they were. So many of these things in the old papers, they'll describe things and not tell you where they were. I don't know if they were just guarding their secrets or if it didn't occur to them to tell anyone. However, one day we were out, the Geo-Champions were out on a reconnaissance walk to see if we could spot anything we hadn't seen before. And we were on our way back down each way lane, and I looked across into the bushes, and there was a little patch of rock that I hadn't seen before, so I went over and looked at it. And this is after cleaning it, but all we could see at the time was this little area here. And this is what we found. It's these little dimples, which are burrows. And if you use the eye of faith, which I do frequently, you can pair them up. So these could be Diplocraterian, in other words, U-shaped burrows, but we've never seen one in a longitudinal section, and we're not going to start chipping bits off to try and find one. So I'll leave you to decide whether or not it's factual. But those are worm burrows, and we haven't seen them anywhere else in the entire Lickey Hills. So why are they there and nowhere else? Well, I've got an idea, as I've got ideas about lots of things. This is the slab we were just looking at here, and if we follow the bedding plane across to see what's immediately above it, this is what we see. If you look carefully, you can see this is undercut here because the material in there is much softer. It's almost black in colour. You can pull it out with your finger, but it's sandy. And it's a black sand in a clay matrix. And here is a white, more or less pure clay. And I think this is likely to represent a volcanic ash deposit, the black sand, which has blanketed the seafloor. It's killed the worms in situ, and then it's prevented any bioturbation of the sand in which the burrows lie, and protected it from mechanical agitation as well. So I think it's just a fortuitous event, a one-off event, that has preserved them there and nowhere else. So, where else can we see evidence of the environment of deposition? Well, Warren Lane Quarry provides scope. This is used as a storage site by the rangers. So it's not open to the public, but you can get permission from the rangers to go in. Redditch Memoir says, sorting grain-shaped sedimentary structure of the rock suggests deposition in a high-energy marine environment. And you can see some evidence of this. We've got symmetric ripples. You see this little ridge crest here and not here. Well, they're not brilliant, but they are there. So we've got a wave-agitated environment. We've also got asymmetric ripples. Here's the ripple crest curving around here. So we've also got current flow, in this environment presumably tidal flow. And we've got this channel structure which has got cross-bedding in it. These faucets are dipping away from us, suggesting a stream flow, a current flow in that direction. But one really nice feature was identified by one of the group a couple of years ago now, and that's this. So this little double ridge structure, a Cruziana, a feeding trace from a trilobite, and trilobites are exclusively marine, so there's the proof, if you need it, that this was a marine environment. If you want to see this, I would rush over tomorrow, because when we looked at it the other day, it's falling apart, and it's not going to be there by the summer, which is a shame. So, in the quarry, it was used as a testing site for field guns in the First World War and for small arms in the Second World War. And there's the remains of an ammunition store that was cut into the quarry face. And this is the corner of that building. So this is a right angle in here. We've got normal Lickey quartzite. We've also got a more distinctive reddish coloured pebbly sandstone which bridges across to the other side. It's the same layer. If you look along the strike, this is actually the same layer. Here it just forms a wedge that pinches out before you get to the base of the outcrop. And there was some discussion about whether this was a sedimentary layer that was the same age as the Lickey quartzite, like a storm deposit, or if it was something quite different. And I initially favoured the idea that it was a sedimentary deposit, a storm deposit, and went out to prove it, and it proved exactly the opposite in the process. Here it is. This is the reddish sandstone going up here. And if we look just here, this is the reddish sandstone, and we've got angular fragments of Lickey quartzite inside it. So the Lickey quartzite had already been formed, it had been buried, it had been uplifted and then broken up into fragments and incorporated into a much more recent sandstone. This is across the structure into the opposite corner. This is the tapering bit of, this is the tapering wedge of that same deposit, which is clearer if I colour it in. And if we look down at the bottom end, again, we find angular fragments of Lickey quartzite within the structure. So once again, we've got lithified fragments being broken off and incorporated into a younger deposit. Here we're looking across the structure. So this is the one outcrop, and we look across the corner of the ammunition store to the tapering wedge of material. So the dip of the bedding is going top right to bottom left. And if we look here at number 1, we see this. I've coloured the red sandstone to show it more clearly. And this is where a bed is broken through, and then the reddish sandstone has been deposited against that fracture. So what brought the reddish deposit in? Clearly, this must have been an open fissure that sediment got brought into. So was the sediment blown in or was it washed in? Well, at number 2, we've got this little pebble. Nice, we find these from time to time. A nice rounded vein quartz pebble that's been brought in. Clearly this wasn't blown in, it must have been washed in. So it's presumably fluvial activity that's washed it in. I say presumably, you'll see why shortly. In contrast to that, I've only ever seen one pebble in the Lickey quartzite itself, and it's just there. There it is. And you can see that the fracture has broken through the pebble such that the pebble is now flush with the Lickey quartzite. There's no distinction in the hardness and resistance of the pebble or the surrounding rock material. In contrast, this is the reddish sandstone, and you can see the sand grains weathering out, standing proud. They haven't been broken through. This is a lump of Lickey quartzite, greyish in colour, and these sand grains have been broken through where the fracture has gone. They're so well cemented in that rather than the break going around the grains, it goes through them. In contrast with this, the reddish sandstone, you can see the grains standing proud. They're well rounded, and I would claim that they've got a frosted surface appearance. Ian Fairchild tells me that you can't say they're aeolian unless you get an electron micrograph and examine the abrasions on them to be sure. But again, I've got the eye of faith. And to me, those are aeolian grains. So the most likely origin for those, if you look at the surrounding geology, is Permian aeolian deposits. But we've got pebbles in it, suggesting they've been washed in by water, making it more likely that the fissures were infilled during the Triassic. You may say that's speculative, but I'll give you more evidence in a minute. So that's the Lickey quartzite in thin section under the microscope. You can see that we've got these sutured joints between the grains, suggesting a depth of burial of at least 1 kilometre. In contrast, the reddish sandstone, we've still got the smooth, rounded outlines of the grains. So a much shallower depth of burial, and we've still got matrix material in between the grains. So it hasn't undergone the same depth of burial as the Lickey quartzite, so it must be younger. So if this red wedge here is a fissure infill, it was open to the surface, so it must be part of an unconformity. So where do you look for the rest of the unconformity? Well, you go up the hill, don't you? So here's Warren Lane, where we were just looking, and if you climb up the hill, Bilberry Hill, you come to another outcrop. Hardy remarked on this, some unusual examples of brecciated quartzite, which have been strongly cemented by quartz following brecciation crushing. I love disproving the old geologists. It's great. Are of particular interest. These are strongly resistant to erosion and have and form small but conspicuous masses standing about a metre above the general level of the quartzite. And here they are, as they were. These Edwardian ladies are sitting on said boulders. And if you notice the one they're perched upon, the scenery has changed somewhat, but the boulders are still there. This is the one they were sat on. Erosion has removed some of the material around, but they're still recognisable. So there was discussion with concerning these. There's breccia there. Is it structural breccia caused by crushing, as Hardy would have it? A lot of people said, oh, well, it's the hinge of the anticline. Anticline, that makes it sound far too simple. It's not that simple. But we've seen type folding in Bark Green Road Quarry that hasn't produced that sort of pattern of brecciation. Or is it a sedimentary breccia? And the other point of contention, was this outcrop or were they just loose boulders? Well, I reckoned that they were outcrop, and I was quite sure that they were sedimentary. If we look here, I've highlighted this one fragment. So we've got a 20 centimetre fragment, very angular. It's travelled no distance at all. It's just broken off the outcrop and been incorporated into the breccia. If we look at this rock here at 4A, here's the bits of Lickey quartzite in a sandy matrix. And if you look carefully, you can pick out very well rounded sand grains, rather similar to what we saw in the Fisher infill. So I reckoned if it was a sedimentary breccia, if we dug down and did some pressure washing, we would find an unconformity. And this is my James Hutton moment, predicting an unconformity and then finding it. And this was our first view of the unconformity. Lickey quartzite below, breccia above. This is what the Lickey quartzite looks like there. Again, we've got little cavities where feldspars have weathered out, which will become significant very shortly. I've darkened the breccia so you can see the distinction between the two more easily. Hard, grey, Lickey quartzite, and irregular patches of the breccia. But in contrast to this very well cemented Lickey quartzite, at a slightly deeper depth, we've got this really well jointed quartzite. You can just pull the blocks out with your hands. So there's something odd going on here. And if we look round the other side of this boulder, we can see why. Again, I've darkened down the breccia to make it clearer. This was the first bit of the unconformity that we saw previously. We've got a very clear unconformity going across here. But interestingly, the Lickey quartzite at a depth of about 20-25 centimetres is undercut all the way around. It's following the shape of the unconformity, but it's undercut because under here you can see those fragments in there. Those are loose, well-jointed fragments that you can pull out easily. So, in fact, this is a silcrete. What's happened is that the breccia and the top 20 centimetres of the Lickey quartzite have been reinforced by a silica cement being precipitated in the rock. And then it only extends down 20 centimetres or so into the Lickey quartzite, which suggests something about the origin of it. Now, this is very similar in many respects to the unconformity on Arran, Hutton's unconformity on Arran, except some slight differences. This is Hutton's unconformity there. We've got Dalradian phyllites, and you can see this sort of slate-like structure. We've got a very steep foliation in the phyllites down here. Above, we've got, they're described as cornstones. It's just a conglomerate that's been cemented with calcium carbonate, calcite. So this was a very dry environment. Groundwater was being drawn up to the surface during long periods of drought and evaporating, and calcium carbonate was being precipitated. But it didn't just precipitate in the conglomerates, it precipitated in the phyllites. And you can see here that very steep foliation, but it's a lot harder than the unreinforced phyllites below. And the unwary geologist will come along and say, there's the unconformity there. But it's not, it's actually there. That's the unconformity. So we've got a similar situation on the top of Bilberry Hill, except that instead of calcium carbonate being precipitated, silica has been precipitated. And this is the simplest model for this. There are various ways in which silcretes can form, but this is the pedogenic model. In other words, pedo for soil processes and genic for origin. So soil origin forming at the Earth's surface. So imagine this is the exposed Lickey quartzite, and it suffers weathering. We get an accumulation of breccia on the top. The water passing through the quartzite weathers the feldspars, releasing significantly silica in solution. So we end up with silica-enriched groundwater. And then during periods of drought, water is drawn up by capillary action and evaporates at the surface, but obviously the silica doesn't evaporate. It remains behind. It precipitates in the surface layers. So both the breccia and the underlying 20 centimetres of Lickey quartzite gets impregnated and forms a very, very resistant cap rock on top of the hills, limiting the amount of erosion, or at least the rate of erosion, that subsequently occurs. So we've got this on Bilberry Hill. Have we got it on Rednall Hill? Well, John, you found this, didn't you? John and Julie were out for a walk one day, and John spotted that in the path. And it's a little patch of breccia. So we excavated, we pressure washed. And sure enough, there it is. There's the breccia. There's the reinforced Lickey quartzite. And there's the unreinforced Lickey quartzite below. So we've got this silcrete capping on Bilberry Hill. We've got it on Rednall Hill. And all around the area, at the base of the hills, we find these fallen blocks of the same stuff. Each of these has got the unconformity in it. So there you can see the unconformity there. The unconformity's there. The unconformity I'll show you in a moment. It's just underneath there. This lump here is on the table, so you can touch and feel the unconformity. I brought it with me. And notice this is from Cofton Hill, the southern hill, and we find quite a few of these around Cofton Hill. We've not seen outcrop because it's so heavily vegetated on the top of Cofton Hill, but it's there, we know, because the blocks around it provide evidence. So this is the one at the north end of Rednall Hill. This is a fallen block, and clearly you can see the breccia above and the Lickey quartzite below, and the clear unconformity between the two. But it's all silcrete. And as I say, this is the one that I've got here with me, which you can have a look at more closely. So we've got silcrete, silcrete, silcrete. And remember, this is a cap rock limiting the rate of erosion. Is it Triassic? I believe so. So we know, received wisdom, that the extensional phase that caused the Worcester Basin and the Knoll Basin to occur happened during the late Permian. So this is when that horsed block would have emerged. Excavations in Tessel Lane, which is just off to the northeast of the northern end of the Lickey Hills, provided evidence of breccia of Lickey quartzite fragments interbedded with Triassic sediments. And almost certainly the local source of these must have been the Lickey Hills themselves. So we know the Lickey Hills were exposed during the Triassic and being eroded. So it seems most likely that the Silcrete itself is of the same age. I won't labour that. All of these references you can find yourself. So this is what the solid geology map looks like currently, but I would suggest to you that perhaps it should look more like this. So on top of the existing Ordovician, we've got a new deposit of Lickey breccia, Triassic Lickey breccia, capping the hills. Now, I'll take you back to the fractures. Now, we're back to the Kendall End quarry at the southern end of the hills, and we've already seen sediment-filled fissures in Warren Lane quarry. Well, in Kendall End, we've got lots of fissures, and different sorts. That's just a fault, common or garden fault, with fault breccia in it. This is one of those clay-rich layers along which movement has occurred, and this is the one which has got the mica above the clay instead of below it, suggesting that it's inverted. But we've also got, come here, at number 2 and 5, which is linked to 4, we've got fissures that cross-cut the bedding. And if we look at a sample from there, it looks like this. You can see rounded pebbles in it. And if we look more closely, you can pick out nicely rounded, well-rounded, frosted grains that I would suggest are, have experienced at least aeolian transport. But clearly the presence of pebbles tells you that it's been washed in by water. And at Rose Hill, we've got fissures. Take a sample, and again, some nicely rounded grains with frosted surface texture, suggesting the same origin. I'll take you back to Lickey Gorge, which I mentioned before. North is over this end now. I've reversed it. This is an old LiDAR image draped across the Google Earth terrain. And at that time, the coverage wasn't complete, which is why it abruptly ends. And the colours just relate to altitude. But the Rose Hill quarry fissures that we just saw are there. And last year, I discovered another infilled fissure on the south side of the Lickey Gorge here. Now, one possible previous interpretation of this, it was suggested that this was a glacial outwash feature. It was an overspill from an ice-dammed lake that had cut this gorge. Well, if you can accept that the sediment that's inside these fissures is Triassic in origin, then this gorge must be a Triassic feature. So, this is a similar feature, gives you an idea of the sort of landscape that we had in the Triassic. This is Newcliffe Quarry in Leicestershire, and the red sediments are Mercia mudstones, filling a very similar valley feature to the one that we've got in the Lickey Hills. So it's not inconceivable that this sort of feature could have developed in the Lickey Hills at the same time. So this is a more recent LiDAR image draped across the Google Earth terrain. And this is the Lickey Gorge we're talking about. So we've got sediment-filled fissures there and there, as well as the ones in Warren Lane Quarry there, and Kendall End Quarry down here. So we've got sediments being washed off the Lickey Hills. We know the Lickey Hills were uplifted at this time because we've got breccias, sedimentary breccias, in the local area that have been washed down from those hills. And at the same time, we've got fissures around the base of the hills that are filled with what appear to be Triassic sediments, which suggests that the shape of the hills that we've got now is broadly similar to what they were all the way back in the Triassic, that they were buried with softer sediments that have now been eroded away, but in particular, the silcrete capping on the rocks has protected them from deeper erosion. So it strikes me that this could represent an exhumed Triassic landscape, that what we're seeing in terms of the terrain of the Lickey Hills is more or less the same as it was back in the Triassic. And that's as far as the research has got. If you want to read more, you can read the outdated version of this book, because I haven't updated it yet. You can immediately see that the title says the Lower Paleozoic Geology of the Lickey Hills. This was before the idea of the breccia being Triassic in age, so it needs to be completely updated. There's lots of stuff that's missing from it. But it also contains not just the information that we've found in the Lickey Hills, but I tried to compile all the information from different sources that we already knew, because it saves hunting around in different sources. So you can download that from the Champions website using that QR code, or just search for it on the Champions website. I've got a printed copy here if you want to have a browse through it. You're very welcome to. So that's it. So with thanks to the Hereford and Worcestershire Earth Heritage Trust, the Lickey Hills Rangers, and of course, fellow members of the Lickey Geo-Champions. That's all I know.
Yes, Alec, falls to me to do the formal bit, which is to give you our formal votes of thanks for a wonderful insight into modern amateurs' contributions to fieldwork. And it strikes me there's two things really on this. One is, unless you go looking you don't find, and people who care and who know the area best are probably always have been well suited to finding the curious things that don't fit the normal explanations. So that's a real plus for you Geo-Champions. The second thing is, isn't it lovely to have some modern technology that allows us to make comparisons in a way that perhaps our forebears were unable to. But they had better quarries actively creating exposure. Yeah. So in a balanced way, we are adding new knowledge to a fairly reliable old-timers knowledge. But that was a wonderful insight into field evidence and how you slowly but surely accumulate the evidence that allows you to form a complex interpretation of something which, in the case of the Lickeys, is pretty complex. So would you mind joining me all in saying the usual thank you to our speaker tonight? Well done, Alan.